September 10, 1918. Summit of Pikes Peak, Colorado, 14,115 feet above sea level. The scene was absurd. A 350 horsepower Liberty V-12 aircraft engine, the workhorse of America's nascent Air Force, sat bolted to a steel test stand on the back of a Packard truck. Around it, Dr. Sanford Moss and a crew of shivering technicians worked in thin mountain air, their breath freezing instantly in the Colorado autumn. They had hauled this entire contraption, engine, dynamometer, propeller, and measuring instruments, 1,300 miles by train from Dayton, Ohio, then driven the Packard 23 miles up an unpaved mountain road to reach this desolate rocky plateau. The reason? To test Moss's turbosupercharger, a device everyone else had given up on. When they fired the Liberty engine without the turbocharger, it coughed pathetically, producing just 230 horsepower, barely two-thirds of its sea-level rating. The massive propeller turned sluggishly. In the thin air at 14,000 feet, the engine was suffocating. Then Moss engaged his device. Instantly, exhaust gases roaring through the turbine spun a compressor at 20,000 RPM. The compressor forced dense air into the cylinders. The engine's labored cough transformed into a steady roar. Power surged to 356 horsepower, more than it had produced at McCook Field in Ohio near sea level. The turbine housing glowed cherry red at over 1,500 degrees Fahrenheit, radiating heat in the freezing mountain air. The contrast was surreal. Ice formed on the test equipment, while inches away, metal glowed like molten glass. Moss's notes from that day were characteristically understated. Maximum horsepower of 377 measured for 30 seconds before spark plug failure. 4-hour endurance test at 313 horsepower successful. What he'd proven that September day would save thousands of lives 2 decades later. Without the turbo supercharger, America's strategic bombing campaign in World War II would have been impossible. The B-17 Flying Fortress, America's most famous bomber, would have been grounded at altitudes where German fighters could shred it. This is the documented story of how one engineer's obsession with exhaust-driven turbines created the technology that gave America air supremacy, and how those glowing red devices, visible for miles at night, became beacons of hope for Allied pilots and targets of terror for their enemies. Sanford Alexander Moss was born August 23, 1872 in San Francisco. He studied mechanical engineering at the University of California, focusing on steam turbines, the cutting-edge power technology of the 1890s. But Moss was ahead of his time. His master's thesis proposed replacing locomotive piston engines with gas turbines, an idea so radical his professors questioned his sanity. Steam locomotives worked. Why mess with success? In 1903, Moss completed his doctorate at Cornell University with a dissertation titled The Gas Turbine, an Internal Combustion Prime Mover. He built America's first functioning gas turbine in Cornell's laboratory, burning fuel under pressure to spin a turbine wheel. It worked, barely. The temperatures melted the turbine blades. The efficiency was terrible, but it proved the concept. General Electric hired Moss that same year for their steam turbine department in Lynn, Massachusetts. He worked alongside legends Elihu Thomson and Charles Steinmetz, developing turbines for electrical generation. GE allowed Moss to tinker with his gas turbine obsession, but without high-temperature metals, his designs remained laboratory curiosities. Then came World War I, and suddenly Moss's pinwheel had military relevance. Aircraft engines lost power with altitude, approximately 3% for every 1,000 feet climbed. At 10,000 feet, a 400 horsepower engine produced just 280 horsepower. At 20,000 feet, barely 200 horsepower remained. This meant bombers couldn't climb high enough to avoid ground fire, and fighters couldn't catch enemy aircraft operating at altitude. French engineer Auguste Rateau had built experimental turbo-superchargers before the war, using exhaust gases to spin a turbine driving an air compressor. But the devices exploded spectacularly. The turbines, spun by 1500 degree F exhaust at 20,000 plus RPM, disintegrated from centrifugal stress and heat. Rateau gave up. In November 1917, William Durant, chairman of the National Advisory Committee for Aeronautics, NACA, predecessor to NASA, contacted GE President E.W. Rice with an urgent request. Could Sanford Moss make Rateau's concept work? Moss had exactly the right background. He understood turbines, he understood compressors, and he was stubborn enough to solve problems others deemed impossible. By June 1918, GE's Lynn facility shipped a prototype turbo-supercharger to McCook Field in Dayton for testing on the Liberty 12. The device worked, but barely. Excessive heat caused persistent failures. Turbine blades cracked, housings warped. That's when Moss proposed the Pikes Peak demonstration, not to prove the concept, he knew it worked, but to prove it could work reliably at high altitude, where it mattered most. The mobile laboratory that arrived in Colorado Springs in August 1918 looked like a carnival contraption. The Liberty engine sat on a Packard truck bed, connected to a dynamometer, torque measuring device, and a massive propeller to absorb power. The turbo supercharger, a bulbous metal housing containing turbine and compressor wheels, sat beneath, connected by exhaust pipes and intake plumbing. C.P. Grimes from McCook Field and a crew of technicians joined Moss for the ascent. The Pikes Peak Auto Highway, opened in 1916, was barely a road, unpaved, narrow, with hairpin turns and 1,000-foot drop-offs. The Packard, weighted down with engine and equipment, chugged upward for hours. At the summit, a rocky flat 300 feet across, they set up the test rig and began 4 weeks of systematic experiments. The challenges were immediate. Carburetor jets clogged with altitude. The fuel-air mixture, calibrated for sea level, ran too rich in thin air. Exhaust manifold joints leaked under thermal cycling. The metal expanded when hot, contracted when cold, opening gaps. Compressor housing cracked from casting flaws stressed by pressure. Thrust washers broke from vibration. Spark plugs failed repeatedly from the extreme combustion pressures created by forced induction. Yet, over 25 test runs, Moss and his team systematically solved each problem. They rejetted the carburetor. They reinforced manifold joints. They replaced the cracked compressor housing. They redesigned thrust bearings. The breakthrough came on September 10th. With the turbo supercharger fully optimized, the Liberty engine at 14,115 feet produced 377 horsepower for 30 seconds, 106% of its rated sea level power. Even accounting for spark plug limitations, a sustained 313 horsepower during a 4-hour endurance run proved the concept viable. Moss left no record of celebration, but everyone present knew they'd witnessed history. An engine breathing normally in air so thin humans gasped for every breath. The Pikes Peak success should have launched mass production. Instead, the turbo supercharger almost died. World War I ended November 11, 1918, 2 months after the mountain test. Orders for warplanes evaporated. The Army canceled contracts. GE's turbo supercharger program shrank to a skeleton crew. In July 1919, a Lapierre biplane equipped with a turbocharged Liberty engine flew for the first time. It hit 137 miles per hour at 18,400 feet, 52% faster than without supercharging. The plane went on to set altitude records, reaching 40,000 feet in 1921, double what naturally aspirated engines could achieve. But peacetime military aviation was a backwater. Budgets were slashed, innovation stopped. The few turbo superchargers GE produced were experimental units for record attempts and testing. Moss kept the technology alive through sheer will. He developed geared mechanical superchargers, driven by the engine rather than exhaust, as a compromise, less efficient than turbos but simpler. These found wider acceptance on radial engines, like those built by Pratt & Whitney and Wright Aeronautical. Throughout the 1920s and early 1930s, Moss experienced what he called the glassy eye from GE executives questioning whether aviation would ever provide significant business. More than once, budget cuts nearly eliminated the aviation department entirely. Then, in 1933, Adolf Hitler became Chancellor of Germany. By 1935, Germany openly rearmed in violation of Versailles Treaty restrictions. The Luftwaffe, officially disbanded after World War I, reformed with modern aircraft, fast Messerschmitt Bf-109 fighters, and Junkers Ju-87 Stuka dive bombers. America, watching Europe slide toward war, began rearming. And suddenly, Sanford Moss's two-decade-old invention became critical. The Boeing Model 299, prototype for what would become the B-17 Flying Fortress, first flew July 28, 1935. It was revolutionary. All-metal construction, 4 engines, massive bomb load, defensive armament, earning it the Flying Fortress nickname. But it had a fatal flaw: insufficient altitude capability. Early B-17s used standard mechanically driven superchargers, gear-driven compressors that forced air into engines. These worked, but inefficiently. The gears sapped horsepower from the engine to drive the compressor. At high altitude, the compressor consumed so much power that net engine output barely increased. The B-17C and B-17D models, entering service in 1940, had service ceilings around 25,000 feet. Loaded with bombs and fuel, they struggled to reach even that altitude. This put them squarely in the killing zone for anti-aircraft flak, effective from 15,000 to 30,000 feet, and well within range of German fighters. The Army Air Corps needed bombers capable of operating at 30,000 plus feet, above most flak, where thinner air hindered interceptors. But how? In 1937, the Air Corps placed an order with GE, develop turbosuperchargers for the B-17. This wasn't a research project, it was a rush production order for immediate deployment. The call went out to Sanford Moss. He was 65 years old and officially retired. He came back anyway. The fundamental problem that had plagued turbosuperchargers since 1918 was heat-induced material failure. Exhaust gases hitting the turbine wheel exceeded 1,500 degrees Fahrenheit, hot enough to melt many metals. The turbine spinning at 20,000 plus RPM experienced enormous centrifugal stresses. Any weakness caused catastrophic failure. The turbine would disintegrate, throwing shrapnel that could sever control cables or puncture fuel tanks. Between 1920 and 1937, metallurgy finally caught up to Moss's engineering vision. Haynes Stellite Company developed cobalt, chromium, tungsten alloys that maintained strength at high temperatures. Inconel, a nickel-chromium iron superalloy developed in the 1930s, provided oxidation resistance at extreme temperatures. Molybdenum additions improved creep resistance, the tendency of metals to deform slowly under sustained stress and heat. These advanced alloys allowed turbine wheels to survive sustained operation at temperatures and speeds that would have destroyed 1918-era materials within hours. The GE Type B2 turbosupercharger, developed in 1937 to 1939 specifically for the B-17, incorporated these materials. The turbine wheel, machined from high-temperature alloy, measured approximately 9 inches in diameter. The compressor wheel, also 9 inches, compressed intake air to boost pressures exceeding atmospheric by 5 to 8 psi. But the B2 wasn't just a turbine compressor unit. It was a complete pneumatic and thermal management system. Exhaust ducting ran from the engines, mounted in wing nacelles, to the turbo-supercharger units mounted beneath the wings. This plumbing had to withstand 1,500 degrees Fahrenheit exhaust while flexing with wing movement and vibration. Intercoolers cooled the compressed air before it entered the engine. Compressed air heats up from the physics of compression, not friction. Hot air is less dense than cool air. Cooling the compressed air before intake increased density further, improving power. Wastegates controlled boost pressure. At lower altitudes, the thin exhaust stream couldn't spin the turbine fast enough to generate useful boost. But at high altitude, with the engine working hard, too much boost could cause detonation or premature fuel ignition, destroying pistons. Wastegates, adjustable valves in the exhaust, let pilots control how much exhaust hit the turbine. The entire system added significant weight and complexity to the aircraft. Each B-17 carried 4 turbosuperchargers, one per engine, plus miles of ducting, intercoolers, control linkages, and oil systems for turbo bearings. The weight penalty was hundreds of pounds, but the performance gain was revolutionary. In 1939, the Y-1 B-17A flew, a B-17 testbed equipped with GE Type B turbosuperchargers. The test pilot climbed to 30,000 feet. At that altitude, unassisted engines would have been producing perhaps 40% of sea-level power, wheezing, struggling, barely keeping the heavy bomber aloft. But with turbos engaged, the Wright R-1820 Cyclone engines roared at nearly full power. The B-17 accelerated to 311 miles per hour, faster than many fighters at sea level. The pilot looked down at clouds that would have been above him in earlier bombers. Whether that forced other aircraft to divert or abort became irrelevant. The B-17 simply flew over it. More importantly, the bomber could maintain altitude even under combat conditions, taking evasive action, flying through turbulence, absorbing battle damage. Other bombers, operating at their maximum ceiling, had no performance margin. Any problem, damage, weather, combat maneuvers, forced them down into flak zones. The turbocharged B-17 had performance to spare. It could fight, maneuver, and survive at altitudes where the enemy struggled just to reach it. Production orders followed immediately. By 1941, every B-17E and later model incorporated turbochargers as standard equipment. The Flying Fortress had finally found the altitude capability that made its Fortress nickname meaningful. But there was a problem nobody had anticipated. At night, turbosuperchargers were visible for miles. Lieutenant James O'Malley, a B-17 pilot with the 303rd Bomb Group, later described what every night mission pilot knew. Looking out from the cockpit at 25,000 feet in darkness, you could see your own engine's turbochargers glowing beneath the wings, dull red at cruise power, bright cherry red at full power. Each of your 4 engines had a turbo supercharger housing, glowing like a small sun. And you could see every other B-17 in the formation, each marked by 8 glowing points, 4 turbos visible from above and below. The turbine housings, heated by exhaust gases, reached temperatures of 1,500 to 1,700 degrees F. At full power, they glowed incandescent red, visible from miles away against the black night sky. For German night fighters prowling the darkness, turbo superchargers were perfect aiming points. Luftwaffe pilot reports routinely mentioned following the red eyes of American bombers. The psychological impact on crews was profound. You were flying a machine with 4 glowing furnaces attached to your wings. If a fuel line developed a leak, common from flak damage or vibration, gasoline would spray onto 1,700 degrees F metal. The result was instant catastrophic fire. B-17 crews learned to watch their turbos obsessively. A turbo glowing brighter than normal meant a runaway. The wastegate had failed closed, forcing all exhaust through the turbine, overspeeding it until it exploded. A turbo that suddenly dimmed meant failure. Loss of boost at high altitude could cause the aircraft to lose altitude into flak zones. Yet, despite the vulnerability, nobody seriously considered removing the turbos. Without them, the B-17 couldn't perform its mission. The glowing red housings were the price of flying high enough to survive. German aircraft used different technology, mechanically driven superchargers with sophisticated multi-stage designs. The Messerschmitt Bf-109G used a 2-stage supercharger driven by gears from the Daimler-Benz DB605 engine. This provided good power at altitude, certainly enough for the Bf-109 to intercept B-17s. The Focke-Wulf FW190 initially used a BMW 801 radial engine with an advanced multi-stage supercharger. Later variants, FW190D, switched to the Junkers JUMO 213 with two-stage supercharging plus MW50 methanol water injection for emergency power boosts. These systems worked. German fighters could reach 30,000 plus feet, but they had a critical limitation: parasitic power loss. A mechanically driven supercharger consumes engine power to operate. The gears, shafts, and compressor wheel absorb horsepower that would otherwise drive the propeller. At high altitude, where the supercharger must work hardest, compressing very thin air, it can consume 25 to 30% of engine power. The GE turbosupercharger was fundamentally different. It ran on waste energy. Exhaust gases, which would otherwise be expelled uselessly, spun the turbine. The power to compress intake air came free from energy the engine was discarding anyway. This meant at high altitude, the turbocharged B-17 engines retained more net power than German engines, working against parasitic supercharger losses. A German fighter climbing to intercept burned enormous fuel and expended maximum engine power just to reach the bomber's altitude. When it arrived, it had limited time and energy for combat before fuel ran low or the engine overheated. Meanwhile, the B-17 cruised efficiently at 30,000 feet, its turbos effortlessly maintaining power, able to sustain formation for hours. Operating at 30,000 plus feet meant entering an environment hostile to both men and machines. At 32,000 feet, a typical B-17 combat altitude, outside air temperature was routinely -50 degrees to -60 degrees Fahrenheit, -45 degrees Celsius to -51 degrees Celsius. Metal became brittle, oil congealed, control cables stiffened, hydraulic fluid thickened. The turbo supercharger systems, despite their glowing housings, were not immune to cold. The wastegate control linkages, cables and rods connecting cockpit controls to wastegate valves, could freeze solid. When this happened, pilots lost boost control. Either the wastegate froze open, no boost, loss of power, or froze closed, runaway boost, engine detonation risk. The oil lines feeding turbo bearings were vulnerable. Despite being close to hot exhaust, at altitude, the intense cold could congeal oil in lines just inches from 1,500 degrees Fahrenheit metal. Without lubrication, turbo bearings would seize, destroying the turbine. Gunners and maintenance crews face nightmarish conditions. B-17s had an open bomb bay, not pressurized, not heated. When a turbo malfunctioned in flight, someone had to climb into the bay, work in -60 degrees Fahrenheit air at 30,000 feet without oxygen, bomb bay was unpressurized, and attempt emergency repairs. Frostbite occurred in seconds. Touching bare metal with ungloved hands meant instant flash freezing of skin to metal. Men returning from these emergency repairs often had blackened fingers that would later be amputated. Yet they did it, because the alternative, losing boost and having to descend into the flak zone, was almost certainly fatal for the entire crew. Another unintended consequence of high-altitude turbocharged flight was contrails. Condensation trails formed when hot exhaust hits extremely cold air. The turbo superchargers produce particularly dramatic contrails. The exhaust, already hot from engine combustion, was further heated passing through the turbine. When this 1,500 degrees Fahrenheit plus exhaust hit -60 degree Fahrenheit air, water vapor and the exhaust instantly condensed and froze into ice crystals, forming long white trails behind each aircraft. These contrails were beautiful and deadly. They announced bomber formation's position to any observer within 100 miles. German fighter controllers used contrail reports to vector interceptors to bombers long before radar contact. Bomber crews desperately wanted to avoid contrail formation. But physics was unforgiving. The specific combination of exhaust temperature, ambient air temperature, and humidity determined whether contrails formed. At certain altitudes, typically 25,000 to 35,000 feet, contrails were unavoidable. Some missions could be flown under the contrails, below the altitude where they formed, but this often meant flying lower, where flak was more effective. Other missions could be flown above the contrails, but this required extreme altitudes, 38,000 plus feet, that strained even turbocharged engines. Most missions simply accepted contrails as the price of high-altitude operations. The white trails marked bomber streams across Germany, advertising their presence but at least keeping them out of heavy flak range. The Schweinfurt raids of August and October 1943 tested the B-17 and its turbosuperchargers to their limits. Schweinfurt, a city in Bavaria, hosted Germany's primary ball bearing factories. Destroying them could cripple German armaments production, if the bombers could get there. On August 17, 1943, 230 B-17s attacked Schweinfurt in daylight without fighter escort. Fighters lacked the range to accompany bombers deep into Germany. The bombers flew at 27,000 to 30,000 feet, relying on altitude and defensive firepower to survive. The Luftwaffe response was savage. German fighters, using coordinated attacks, shot down 36 B-17s, a 15.7% loss rate. Many bombers returned with severe damage. The October 14th raid, Black Thursday, was worse. Of 291 B-17s attacking Schweinfurt, 60 were shot down, a 20.6% loss rate. Another 17 were damaged beyond repair. The 8th Air Force lost 600 aircrew in a single day. The turbosuperchargers worked flawlessly throughout both raids. Engines maintained power at altitude. Formations held together despite battle damage. But altitude alone couldn't protect bombers from mass fighter attacks by experienced Luftwaffe pilots. Yet, the raids also proved the B-17's survivability. Aircraft hit multiple times by 20mm cannon and machine gun fire made it back to England because their turbocharged engines continued functioning. One B-17 returned with 3 engines out, and the 4th turbocharged engine alone providing enough power to maintain altitude and reach base. Without turbochargers, the Schweinfurt raids would have been impossible to even attempt. With them, the raids were survivable, barely, and demonstrated that strategic bombing of German industry was technically feasible, if costly. The turbosupercharger wasn't limited to bombers. The Republic P-47 Thunderbolt, nicknamed the Jug for its bulbous shape, was essentially a flying turbosupercharger with a cockpit attached. The P-47's Pratt & Whitney R2800 double wasp engine sat in the nose, producing 2,000 horsepower. But to maintain that power at altitude required a GE CH-5 turbosupercharger mounted in the rear fuselage. The installation was engineering madness. Exhaust from the front-mounted engine had to travel through ducting the entire length of the fuselage to reach the turbocharger in the tail. Compressed air from the turbo then traveled forward through more ducting, through an intercooler, and back to the engine intake. This plumbing made the P-47 one of the largest single-engine fighters of World War II. It weighed 17,500 pounds fully loaded, twice the weight of a Spitfire. The bulbous fuselage housed miles of ducting, but the performance justified the size. At 30,000 plus feet, where other fighters struggled, the P-47 turbocharged accelerated. Its top speed at altitude reached 433 miles per hour, faster than most German fighters. More critically, it could dive faster than anything in the sky, approaching 500 miles per hour in steep dives because the turbocharger maintained power even as the aircraft descended. P-47 pilots learned to use this advantage ruthlessly. When bounced by German fighters, they would dive away, knowing no enemy could catch them. They could then zoom climb back to altitude faster than pursuing aircraft because their turbocharger eliminated the traditional altitude performance degradation. By 1944, when P-47s began escorting bombers deep into Germany, Luftwaffe pilots faced an impossible situation. American bombers flying at altitudes German fighters struggled to reach, escorted by American fighters that performed better at those altitudes than German aircraft did at low altitude. The GE turbosupercharger was half a jet engine, literally. A jet engine consists of 1. Compressor, forcing air into combustion chamber, 2. Combustion chamber, burning fuel with compressed air, 3. Turbine, extracting energy from hot exhaust to drive compressor, and 4. Exhaust nozzle, directing remaining exhaust energy rearward for thrust. A turbosupercharger had items 1 and 3, compressor and turbine, mechanically connected. It lacked the combustion chamber and exhaust nozzle because those functions were performed by the piston engine it served. GE's engineers, working on turbosuperchargers throughout the 1930s, accumulated expertise in high-speed compressor design, turbine aerodynamics, and high-temperature metallurgy, the exact knowledge needed to build jet engines. In 1941, the U.S. military obtained British Whittle W-1X jet engine plans. GE was chosen to develop America's version because of their turbo-supercharger experience. The GE I-1A jet engine, Type 1A, drew directly from B-2 turbo-superchargers. The Bell XP-59 Aerocomet, America's first jet aircraft, flew October 1, 1942, powered by 2 GE I-1A engines. The aircraft itself was mediocre, slow, with poor climb rate, but it proved American jet technology was viable. By war's end, GE Aviation became one of the world's leading jet engine manufacturers, producing engines for military and civilian aircraft. The lineage traces directly to Sanford Moss's 1918 turbo-supercharger. Moss, who died November 10, 1946, lived just long enough to see his pinwheel vindicate itself. The device, derided as suicidal in the 1920s, had become the foundation of modern aviation propulsion. Without the GE turbo-supercharger, American strategic bombing would have been impossible. B-17s would have been medium-altitude bombers, operating at 15,000 to 20,000 feet, squarely in the killing zone for anti-aircraft fire. Losses would have been unsustainable. The daylight precision bombing campaign that destroyed German industry would never have occurred. P-47 fighters couldn't have escorted bombers deep into Germany. Without high-altitude performance, they'd have been outclassed by German fighters optimized for lower altitudes, where mechanical superchargers worked efficiently. The entire American strategic air doctrine depended on one invention: an exhaust-driven compressor that could force dense air into engines suffocating in the thin atmosphere above 25,000 feet. That invention came from a stubborn engineer who spent 40 years perfecting technology everyone else abandoned. Sanford Moss, working in a GE laboratory in Massachusetts, turned exhaust waste into horsepower, thin air into dense air, and German fighters' altitude advantage into Allied dominance. The turbo-superchargers glowed cherry red at night, marking bomber formations for German fighters, but they also kept those bombers at altitudes where flak was less accurate, where German fighters struggled to reach, where weather could be flown over rather than through. Imagine the scene in 1944. 1,000 B-17s streaming toward Germany at 30,000 feet, 8 glowing red turbo-superchargers on each aircraft, 8,000 points of red light declaring American industrial might and engineering superiority. German pilots, climbing desperately to intercept, watched those red beacons climb higher, always higher, just out of effective reach. They knew, even before engaging, that the battle was already decided by engineering choices made in peacetime laboratories. Sanford Moss retired in 1938 at age 66. He was called back when war came, refining his turbosuperchargers for B-17s, B-24s, P-38s, P-47s. He worked until his health failed, watching his invention multiply across American skies. When he died in 1946, over 300,000 turbosuperchargers had been manufactured during the war. They had powered the aircraft that destroyed German industry, escorted bombers through flak, and ultimately helped bring the war to an end. In 1953, on the 50th anniversary of powered flight, Lieutenant General James Doolittle, commander of the famous Tokyo raid, placed a monument atop Pikes Peak commemorating Moss's 1918 demonstration. The monument sits near the spot where Moss's Liberty engine, gasping in thin mountain air, proved that exhaust-driven compressors could restore sea-level power at altitude. From that frozen mountaintop to the skies over Germany, from a hand-built prototype to 300,000 production units, Sanford Moss's red-hot turbo supercharger became the breath that saved American air power. The engines suffocated in 1938. General Electric built turbines that glowed red-hot at 1,700 degrees Fahrenheit. And the B-17 Flying Fortress found the altitude where it could truly be a fortress, high above the killing zone, breathing freely in thin air, thanks to exhaust-driven compressors forcing oxygen into cylinders that otherwise would have choked and died. That's the power of engineering, turning waste into advantage, heat into power, and thin air into victory.